Good morning, and thank you for attending our monthly market briefing. Today, we are going to present about the complexity of offload repairs based on the experience we have gathered in ABL Panama in this type of projects. In recent years, Panama has become a very common place in the Americas region for offload repairs, and we will be sharing our perspectives on this topic. Today's learning objectives, firstly, to explain the key drivers influencing the decision-making toward offload repairs. Second, to analyze the current shipyard space limitations in the Americas region. We will be also discussing some emerging shipyard projects in the Americas. Thirdly, to review the key challenges associated with offload repairs. And finally, to discuss through some case studies the impact of project constraints in the final cost of offload repairs. So offload repairs are not the first option for ship owners, and we have identified 4 key drivers toward the decision-making of this type of repairs. Firstly, the availability of dry docking capacity, especially in the short term. Generally, the shipyards capable to accommodate larger vessels are booked several months in advance. So when there is an accident or a failure, it may be very difficult to find a shipyard availability for the repairs. The cost and time of mobilization to a convenient repair facility may be challenging also for the ship owner. The second key driver is the vessel seaworthiness in damaged condition, which is basically decided by the regulatory framework such as the classification societies, the flag state administration, and port state control, which may an assessment of the extension of the damage and may require immediate repairs or may provide a time frame for the repairs. The third key driver are the commercial constraints. Due to charter party obligation, the ship owner may be required to deliver the cargo in a specific time frame, which may be sensitive for some type of vessel, for example, container carriers or gas carriers. Also, temporary repairs may be viewed or may be assessed negatively during vetting compliance and may cause commercial rejection of the vessel, irrespective of the seaworthiness condition at the time of the accident. So this may drive ship owners to carry out permanent repairs, irrespective of their cost. And finally, operational constraints. For example, the vessel loading condition may restrict the vessel from going to dry docking, even if a shipyard space is available. Also, the cargo characteristics, for example, the perishable time or the flammability characteristics of the cargo may restrict the possibility of carrying out repairs or hot work on board. So the dry dock capacity varies to regions worldwide. But in the Americas region, in general, there is a shortage of capacity, and we can see in the map the shipyard capacity or space for larger vessels such as Panamax and upwards. We can see that there is capacity in the northern part of the Americas continent, especially in United States and Canada, both coasts. However, this capacity is basically oriented to the local fleet, especially in the United States, due to the influence of the U.S. Jones Act in U.S. flag vessels. If we go down southward, we can see that in Central America and the Caribbean, we have shipyard capacity in Panama, in the Pacific coast, at the Panama Canal entrance, while in the Caribbean Sea, we can find shipyard capacity in Veracruz, Mexico, in Bahamas, in Jamaica, and Curacao. The Bahamas shipyard is basically focused on cruise ships. In South America, we can find shipyard capacity for larger vessels in Argentina, Brazil, and Chile. In the eastern coast of South America, this capacity is basically focused on offshore vessels, while in Chile, the shipyard is owned by the National Navy, and the priority is towards defense rather than commercial vessels. So if we see the map, we can see that in the Pacific coast, there is a large area between Ensenada, Mexico, up to Talcahuano in Chile, that there is not enough space shipyard capacity set in Panama, when there is one shipyard that was already mentioned. So there is an important need in this part, in this coast in the Americas region. There have been some potential projects that may come in the following years in Panama and in Peru for post-Panamax vessels, but these are still pending to be materialized. So due to this shortage of shipyard capacity, floor repairs are very common in the Americas region, especially in Panama, which is the most important floor repair hub in the Americas, while it is also possible to carry out floor repairs in Jamaica, Curacao, Dominican Republic, and Trinidad and Tobago. So Panama has become an important repair hub in the region. We have, as we mentioned before, there is one shipyard for Panamax vessels in the Pacific entrance of the Panama Canal, which is the only one between Mexico to Chile. But also, there are other important characteristics that make Panama as an important repair hub. For example, there is a local ecosystem with a strong presence of stakeholders, such as the major classification societies. You can find manufacturer representatives from the main and auxiliary systems in Panama. You can find class-approved service providers for firefighting, life-saving appliances, among others. There are 8 floor repair workshops, 4 of them with the capability for carrying out major repairs, including underwater repairs by means of coverland. And this is a very important development in the last years, because 5 years ago, there was only one workshop capable of carrying out complex floor repairs. Every year, around 5,000 afloat maintenance and repair work is carried out in Panama. One workshop is responsible of 60% of this market, while the remaining 40% is distributed between the remaining 7 workshops. Also, every year, there are between 30 to 40 major floor repairs carried out in Panama. Around half of these numbers are related to accidents in Panama Canal waters, while the other 50% are related to accidents and damage occur in neighboring countries, and the vessels sail to Panama as a coming in place for these repairs. So the second driver is the vessel seaworthiness in damaged condition, and we should always question if it's really urgent to carry out this repair. For example, we can see here a case of an oil tanker, Panamax size, which had a contact with the Panama Canal locks during Panama Canal transit. We can see here in the left picture the indentation in the outer shell plate, and we can see also in the right picture the condition of the internal structural members after the accident. And we can see here that the indentation has a small depth, and that there are no cracks or major damage after the accident. So in principle, these repairs may be deferred to a convenient time or to the next periodical dry docking. However, the classification society requested immediate repairs, irrespective that the vessel seaworthiness was not affected or compromised. Also, the ship owner didn't have any request for postponing these repairs toward a more convenient time, and carry out floor repairs in Panama, despite the vessel had to stay 7 days for these immediate repairs. It's probably that the vessel being an oil tanker, the ship owner preferred to carry out permanent repairs in order to avoid any commercial rejection of the vessel during vetting inspections. We can see here another case, a similar vessel, Panamax oil tanker, similar damage case. The vessel contacted with the Panama Canal locks during transit. However, different class society, different ship owner criteria. There was no significant damage, and the repairs were deferred to the next dry docking inspection. So in general, the vessel seaworthiness in damaged condition is assessed by several factors, such as the survivability confirmation, the safety and environmental risk analysis, damage assessment, technical feasibility for departure, and regulatory and operations compliance, which together, considering the convenience of carrying out immediate repairs and the availability of repair facilities, are considered in conjunction with these characteristics that are mentioned in this slide. Also, as mentioned before, there are commercial and operational constraints, such as the vessel loading condition, the vessel itinerary, charter requirements, for example, oil major vetting, and the distance from casualty location to convenient repair facilities, which may drive decisions toward temporary rather than permanent repairs, and vice versa. Here we can see an ideal flowchart towards the decision-making of offload repairs. Firstly, the damage is found on board, or the failure is found on board by the master, the crew, the class society, etc. So the parties, different stakeholders are notified, such as the ship owner, the classification society, the flag state, the port state control, and the insurers. An assessment of the damage condition, including the repair options, is carried out by these parties. So after that, it is questioned, is the seaworthiness compromised? If the seaworthiness is not compromised, then we can go to a cost-effective repair by deferring to the most convenient time, such as the periodical dry docking on any other convenient repair port. If the seaworthiness is compromised, then we should question if there are appropriate dry dock or convenient repair facilities available. If there are facilities available or shipyard space, then we can proceed to a cost-effective repair by a permanent repair. If there are not appropriate repair facilities or dry dock, then we should consider then the offload repairs, we may be a permanent or temporary one. So offload repairs are considered non-cost-effective solution and are only taken into consideration or decided based on the seaworthiness condition and the availability of convenient repair facilities. And these repairs are not cost-effective because of technical and logistical challenge, basically. So let's first start discussing the technical challenge toward offload repairs. And the first one is the work scope definition. For example, the assessment capability to determine the full extent of the damage. This is especially sensitive for underwater inspection. It's sometimes very difficult to identify, for example, distorted panels or the total extension of the damage by divers or CCTV cameras, or from inside the compartments in the double bottom of the vessel. So there is a higher risk for hidden progressive damage when assessing damage in a flood condition. The second challenge is related to the project's critical path. To be able to define a reliable critical path based on the influence of weather and condition, weather and environment in the project schedule, the offshore logistic, and the interdependencies between divers, cranes, boats, access to difficult areas inside the vessel, etc. The third technical challenge is associated with the labor cost management, as the labor cost could be up to 70% of the total repair cost. And also, we may be require more specialized labor force. For example, divers with qualification of underwater welding, which is very rare and generally has a high cost. Another challenge is the operational constraint. For example, the vessel loading condition. If the vessel is fully loaded, then we will have to carry out the repairs in deeper drafts and a difficult environment. Cargo characteristics, there are some cargo conditions that may restrict the possibility of carrying out repairs on board, as well as the local port requirements, which in some part of the world may be challenging to carry out some repairs due to local regulations. So all of these have to be properly managed through a risk management and contingency plan, which has to consider the dynamic conditions of the offshore repair projects, the higher project uncertainty, especially at the start of the project, offshore repair project. The early contingency planning has to be considered at all stages, as well as the stakeholder management, as there are several parties involved, such as the classification societies, the workshop by itself, and other contractors, which may have to be properly managed in order to avoid unnecessary delays. Well, let's talk now about the logistic challenge in offshore repairs. Generally, offshore repairs require simultaneous operations. For example, specific work windows due to environmental factors. If we are carrying out the repairs offshore, conflicting priorities, for example, between the work being carried out onshore in the workshop and the work being carried out offshore alongside the vessel, as well as the increased coordination overhead costs. We have also physical constraints. For example, the offshore transport and crane capacity may limit the size and the weight of some blocks and cofferdam weights. The decision making toward the modular fabrication in the onshore workshop versus on-site fabrication on board the vessel, as well as additional resources for underwater work. For example, the fabrication and transportation of cofferdam and the availability of divers. Geographical constraint has also an important impact in project schedule and cost. For example, the availability of repair berths or the suitable anchorage and shelter work location may have a high influence on the technical solution and final cost. In general, in the Americas region, especially in Panama and the Caribbean, the availability of repair berths is very limited. So generally, the solution is to carry out these repairs offshore. The materials, logistic, and supply chain may be also an important logistic challenge. For example, the transportation of materials to offshore and anchorage locations. Custom requirements may not be the case in Panama. Customs are very expedited in Panama. However, in some countries of the region, this may be challenging considering security related matters, as well as the coordination of the supply chain. Finally, the project integration integrated the work between the workshop and the offshore work, personnel mobilization and demobilization, and alignment with vessel operations are important matters to be considered in this type of projects. So let's analyze some case studies in order to understand the situation that we generally face in offshore repairs. Let's first make the first case study, which is a very successful project in respect to schedule and logistic and technical coordination, despite the high cost of this repair project. So this is a Panamax bulk carrier, which was fully loaded and grounded in the western coast of South America in a very difficult geographical area, with not only because accessibility to the area, but also because this area is very well known because of very low water visibility. So the vessel grounded, and the crew on board had to assess the damage firstly by a sounding of the tanks, and then after carrying out internal inspection from inside the vessel. So the vessel went to offload the cargo and then proceeded from the damaged area to Panama for carrying out the repairs. So the scope of the damage, 8 places were damaged in total, comprising 7 tanks, 5 seawater ballast tanks, 1 fuel oil tank, and 1 diesel oil tank in the bottom of the vessel. So initial constraints, firstly, the grounding event occurred in a very difficult geographical area with no water visibility in the accident location for a proper underwater survey. Immediate repairs requested by class society because of this seaworthiness condition. Too many tanks were compromised in the bottom of the vessel. And as we discussed before, there is no available dry dock in short term in the Pacific coast of the Americas. So the immediate solution has to be done by means of afloat repairs. Some of the technical project challenges. Firstly, the scope of repairs unknown upon vessel arrival. There was no possibility to carry out underwater inspection. So the underwater inspection was done only upon arrival to Panama. So the initial estimation was done only from internal inspection of the compartments by the vessel crew. Second technical challenge, the location of the damage, the vessel bottoms. So underwater repair had to be done as an option. So that means assistance of divers, assessment of the damage by CCTV, by the class society. When you are carrying out identification of damage by divers or even inside the double bottom of the compartments, it is not easy to identify distorted panels, even if you are carrying out the inspection very carefully. So this is a technical challenge also. And poor access and working environment. The damage in different locations in ship bottom, it requires the construction of 8 cofferdams. It has to be properly built, fitted, and monitored through the performance of the project. Logistics challenges. Firstly, finding a shelter location for the repairs. Secondly, optimizing the cofferdam construction. There was required to build 8 cofferdams for this project, so it was a significant, important challenge and cost item for this afloat repair project, and the availability of divers throughout the project. So in this case, fortunately, it was found a repair berth available, which is a cruise terminal in Flamenco Island in the Pacific coast of Panama. If, the repairs were carried out during the low season of the cruise calls. So this facilitates significantly the development of the project, as the effect of weather and environment was minimized and controlled during the repair project. Labor costs for travel and standby time was controlled and minimized, as well as the material transportation logistic managed through the project. We can see here a significant item of this project, which was the cofferdam construction and installation, because the vessel was a bulk carrier, and the vessel was offloaded. There was no cargo on board. There was the possibility to carry out hot work on board in adequate space inside the cargo holds. It was decided to build the cofferdams on the vessel, only bringing the cut section from the onshore workshop, and every cofferdam was built for the vessel, which minimized transportation and logistic cost and crane capacity limitations. So we can see here the construction of the cofferdams. in the left picture, and we can see also in the right picture the cofferland already built and in process to be fitted from the vessel to the water upon construction in order to be fitted in the bottom and start to carry out the respective repairs. So impact on final cost, 8 cofferdams built for the repairs, more than 50 tons of steel used for this construction, which is only done in order to be able to crop and renew the damaged section of the vessel. After that, these cofferdams are basically useless unless the workshop can use it in another future repair project. Time for a floor repair, 45 days. This is from the starting point when the vessel arrived to Panama, carried out the underwater inspection by the class society and with assistance of divers, and a repair plan was properly prepared and carried out. Was completed aligned within the schedule because of the influence of a shelter area plus the repair berth. Repairs were created as permanent by the class society. Final direct cost 10 times or more than 10 times the estimated cost of repairs in dry dock, and 60% of the total cost was related to the cofferdam construction and installation. So we can see here how the underwater floor repairs has a significant increase of cost, unfortunately. And finally, the question if this is the final scope of damage, because as we said earlier, it is very difficult to find distorted panels with assistance of divers and through the internal inspection of the double bottoms. So there is always the possibility that when the vessel is dry docked, some damage are further found, which may be related to this accident. We can see the case number 2, which is an floor repair of cracks in the rudder. Some 4 cracks were found during a periodical underwater inspection assisted by class society. So when the cracks were found, the temporary repairs were carried out, and the class society provided or granted 2 months for the permanent repairs. The vessel was in the Pacific coast of Central America, where there was no availability of dry dock in the short term. So the owner arranged a workshop to carry out a floor repairs, and it was the only repair option available. And the workshop found a berthing facility, but with only the availability of 12 days, because the berth was going to be called by another vessel which was previously programmed. So the repair facility, the port facility said that the repair had to be done in 12 days, and if the repairs were not completed in this time frame, the vessel will be taken out of the port, irrespective if the repairs were completed or not. So a repair plan was established, which was basically to be done in 12 days and required the dismantling of the rudder blade, to place the rudder blade in the repair berth alongside the vessel. There, on shore, to crop and renew the cracked rudder blade sections, to carry out all the non-destructive testing and of the repairs, and then put back the rudder on the vessel. We can see here in the right picture how was the condition of the repair area. You can see here that it was not even necessary to put scaffolding. It was possible to use a cherry picker because we were in a very convenient place for the repairs. However, the rudder could not be dismantled because there was an oil leak in the hydraulic knot in the rudder stock. In order to release the rudder, it was necessary to loosen a rudder knot through hydraulic pressure, and because of these leaks, the rudder could not be dismantled at all times. So after 8 days at berth, the repair plan was aborted, and the vessel was taken to anchorage. After a large significant amount of money invested in this effort and task. So we passed from a port facility, which was shelter area, connection with shore logistics, etc., to going offshore at the Balboa anchorage, 5 nautical miles from shore, with an insignificant increase in labor costs, logistic costs, and uncertainty of the project due to the influence of weather and environmental conditions. And the repair plan has to be changed now to carry out the repairs afloat, carry out all the steel work afloat, offshore. So the vessel had to be trimmed, and a cofferdam has to be built. Around 8 tons of weight of cofferdam has to be built by the workshop onshore, and has to be transported offshore, as we can see in the right pictures. And we have to put this cofferdam in way of the damage area and to carry out all the steel work on this very difficult working environment, as we can see in the lower picture in this slide. Some technical challenges. The location of the damage was in way of the water line, which we required to create a dry condition for the repairs. Age vessel was a 23-year-old vessel. So the feasibility of the first repair plan has to be questioned initially. The contingencies and risk control for the first repair plan and project critical path, for example, was it possible to carry out this repair in this as planned or in 12 days? The influence of weather and environmental condition and anchorage for the second repair plan. In respect to logistics, repairs were carried out in Panama Canal waters, which is manageable, but always has some challenges. For example, you're required to have ACP pilots on board for berthing and unberthing, authorizations, etc. The limited time for using the repair berth for the first repair plan was something which was a challenge. And for the second repair plan, the cofferdam construction and transportation. So impact on final cost. Initial time of repairs for the first repair plan was less than 12 days. Final time for repairs after change of plan and carrying out all this work offshore, 45 days, which caused a significant cost for the ship owner due to the change of repair plan. For example, off-hire time, the ship owner had some contractual arrangement which could not be fulfilled because of the extended time of repairs, etc. Other contingencies due to the long stay during the repairs. In respect to the direct afloat repair cost, the cost was around 6 times the estimated cost of the repairs in dry docking, and more than 3 times the original cost plan for the first repair plan. Finally, we have another case, the final case, which is a vessel that in the Baltic Sea was during sailing, had a contact with an object, and as a result, the propeller tip of some blades were bended. So initial constraints, well, the vessel sailed to the west coast of South America via the Panama Canal, and during the transit, after the transit, on the water inspection was carried out in order to assess the damage. After that, the vessel went to offload the cargo and then came back to Panama for the repairs. So some constraints: no dry docking availability in the Pacific coast. The repair plan has to be approved by the propeller manufacturer, even as per classification rules. Any hot work, each blade had to be completely out of the water as per procedure. And the vessel stability, particularly in light ship, in this case, not possible to ensure an appropriate trim for hot work in the blades. So we can see here the vessel condition after trimming. In order to carry out this repair, the vessel has to be trimmed as much as possible in order to take out the complete blade out of the water, as the intended procedure was to carry out hot straightening of the bended part of the propeller blade. And you cannot carry out hot work if the blades are partially submerged, because will create thermal stresses during the repair work, and this is not allowed. So we can see here that in the lightest trim condition, the blade could not be taken out completely out of the water, and that this required a change of the repair original plan. So some technical challenges: vessel stability characteristics. The trim condition for hot work was not feasible in any trim or light condition of the vessel. Lack of familiarization of repair procedure. For example, the workshop had limited experience in this type of hot work repair. This was the second time the workshop was going to carry out this type of repair. Coincidentally, the previous time, 10 years before, was with me when I was a class surveyor. Communication between stakeholders. For example, the propeller manufacturer opinion was requested only when the vessel arrived to Panama and the repair plan was changed. In respect to logistics, transportation of materials and personnel to anchorage. So impact on final cost: the change of repair plan and communication between stakeholders increased the off-hire time during the repairs. Temporary repairs were completed in 7 days. However, 4 days lost because of communication between stakeholders. So of these 7 days, 3 days were repair work and 4 days were related to waiting time. Repairs considered only temporary, as the blades were cut as a temporary measure, has to be reinstated after that during the next periodical dry docking. And the cost of temporary repairs equal the permanent repairs. Total repair cost at least double due to change of the repair plan. So some conclusions: the drivers toward floor repairs are 4 key drivers, such as the availability of dry dock space, seaworthiness condition, commercial constraints, and operational constraints. There is limited dry docking space in the Americas, especially in the Pacific coast between Ensenada, Mexico, to Talcahuano in Chile. There is only one facility, which is located in Panama. There are some emerging shipyard projects for post-Panamax vessels in Panama and Peru, which are pending of materialization in the following years. For floor repairs, it is always recommended to analyze the urgency of these repairs. Regulatory and commercial pressures or aspects or perception may influence floor repairs, which may be deferred to a more convenient time. Floor repairs have intrinsic technical and logistic challenge, which may have a great impact on the repair schedule and final cost. And final cost of a floor repair may range between 2 up to 10 times the similar cost in dry dock condition. Thank you very much.